All right, so we recently had our lecture on Newton's laws, where we introduced Newton's three laws of motion. The first law said that an object in motion stays in motion, or an object at rest stays at rest, unless acted upon by an outside force. And what that basically meant is that when a force is applied to an object, the object's velocity changes, that's the change in the motion, and thus forces produce accelerations. Newton's second law kind of creates an equation out of the first law. That equation says that the sum of all the forces acting on an object is equal to the mass of the object times its acceleration. And this is the first big equation we're going to discuss, of two. The other one is going to deal with friction, but that's a later lecture. The third law says for every action there's an equal and opposite reaction. And that is a conceptual view that helps certain problems be solved. If you understand that when object A pushes on object B with a certain force, that means that object B must be pushing back onto object A with the same force, but in the other direction. That concept will help certain problems be solved. So you've got a couple of conceptual ideas and a concrete analytical equation to use. And now what this video is going to be about is kind of solving some example problems. So the first example I want to do is we have a nice horizontal floor. A block is sitting on the floor with a mass of 10 kilograms. If you push on this block with a force of, let's say, 30 newtons, and that force is applied at an angle of 60 degrees downwards like this, and then you also push back to the left with a force of 5 newtons, I'd like to find the acceleration. All right. So this is a Newton's law equation because it deals with forces acting on an object, and I want to calculate an acceleration. So that tells me automatically I'm using F equals ma. The first thing I should do is notice that one of the forces in my problem is at an angle, and that's bad. I know forces are vectors, and it's been pounded into my brain that vectors can only be used if they're all in the same direction. So if you have a vector that's at some weird angle, you have to first break that vector up into x and y components. So let me do that first. Let's say we have called this 30 Newton force F1. So F1 will have an x piece, and F1 will have a y piece. The x component of F1, notice the horizontal side is the side adjacent to the angle. So it's going to be 30 times cosine of 60, which is 15. Next, what we want to do is find the y component. So we say, all right, we've got the y piece, that's going to be the side opposite. Opposite goes with sine. So it's 30 times the sine of 60, which is about 26. And that's downward, so we'll call him negative. Notice that applied force is down and to the right. So in the x direction is positive, but in the y direction he's negative. Okay, are there any other forces I happen to know? that are in this problem? Well, yeah. First of all, I know gravity is acting, and the gravitational force acting on my block is mg. That's the force due to gravity. It's called the weight of the object, and it's always mg, and it's always pointing straight down. And then I also know that my block does not want to fall through the floor, so there must be some normal force perpendicular to the floor, in this case pointing upwards, that we'll call the normal force N. And then looking, there's no friction yet. We haven't gotten to the section on friction, so these seem to be all the forces involved acting on my problem. Well, I want to find the acceleration of the block. So I ask myself, in which direction do I think this block wants to move? Is it going to move in the x direction, or the y direction, or some combination? Well, to me, no matter how hard I push, the block is not going to fall through the floor. So I know it's not going to move in the y direction. So there's only one direction it can move in, and that's the x direction. Thus, looking in the x direction, the equation I can use is the sum of the forces in x is equal to mass times the acceleration. Now all I have to do is plug my numbers in. What are all the x forces in my problem? Well, I've got the F1x piece, which is 15 to the right, so that's positive 15 to the right. And I've got the second force of 5 pointing to the left, so he's minus 5. Those are the only x forces in my problem. Set that equal to the mass of the object times its acceleration. And so I just solved this for A. 15 minus 5 is 10. I divide the 10 over 10 becomes 1. So I get an acceleration of 1 meter per second squared. So we see how to solve a Newton's law problem. Given a series of forces acting on the object, I have a force which happens to be at an angle, and if I have multiple forces, then for every force that's at an angle, I break it up into x and y components. After I've done that, I now have all the forces either in the x direction or the y direction. I then look and I try to solve the problem. The problem asks me for the acceleration. I know that the block has to move in the x direction, so that means I only care about x directional forces. In this particular example, there's only two. There's the piece of 30, which is horizontal, and there's the piece of the 5, which is horizontal. Everything that points to the right I call positive. Everything that points to the left I call negative. Plug all the numbers in and I solve for my acceleration. So that's not so bad. Now what I want to do is do an example where things kind of get a little mixed up. And this is a very, very critical example to understand. Oops, black. Example 2. Let's say this time, instead of having my block lie on a nice flat horizontal surface, my block is laying on a ramp. So here's a ramp. The ramp is inclined at 30 degrees. The block is sitting up here, and it has a mass of 10. Now for this particular question, I want to find the acceleration of the block. So I say, well, wait a second. There's no applied forces here. I'm not pushing on the block. I'm not pulling on it. So should the block move? Because after all, Newton's law says the sum of the forces equal mass times acceleration. So if there are no forces, there should be no acceleration. But notice, which is a very important thing for us to be able to do when we analyze a system, is that although we don't explicitly state that there are any forces, we know there must be a force in this problem, and that force has to be gravity. Gravity will always exist in our problems. So I know gravity is pulling down on my block. How does it pull? It always pulls straight down. mg. And now if I think in real life, if I actually have this inclined plane, if I have a ramp and I stick a block on the ramp and maybe the block is made of ice, so there's no friction. What's going to happen? Obviously the block will slide down. The reason it slides down is because of this gravity. This gravity is pulling on the block, making an acceleration. So I cannot say that just because there are no external applied forces by me, this block must not move. It will move, and it'll move not because I'm pushing on it, but because gravity itself pushes on it. Okay. Well, obviously what we have to do here is figure out how in the world are we going to discuss the motion of this object. In our previous examples, the object is free to move in the x direction or the y direction or whatever. Now, if this object moves, it's moving in this angled direction. It's moving along the ramp. And the ramp is in an angle. So if I try to do F equals ma in the x direction, well, that only gives me part of the answer. It only tells me how much it moves in the purely horizontal direction. But it's not just moving in a horizontal direction, it's moving in both the horizontal and vertical directions at the same time. It's moving at this angle. So the way we're going to handle this is we're going to be pretty smart. What we're going to do is say, why in the world do we have to talk about x and y? So far, that's all we've done, is say the big directions in this universe are the x direction and the y direction. But why must it be? God didn't tell us x and y are important. We created it. We made it up. For all we know, our x and y are at angles to some other alien universe or alien civilization, and their x and y are in different directions. So there's nothing universal about the laws of physics that say our x and our y directions are the correct directions. Well, if we think about it then what we can do is, instead of trying to talk about this particular system in either x or y, let me instead talk about two other directions which are equivalent to x and y, but they're at an angle. And the reason I'm going to do it is because the motion of this box will be in one of those two directions. So that is to say, just like this problem, I had an x direction and a y direction that I considered, and my block happened to move in the x direction. Well, for this one, I'm going to have two other completely different directions. Call it, I don't know, x1 and y1. And maybe my block moves in the x1 direction. But x1 and y1 are not the same as x and y in the other example. They're just two other directions. And if I do that, then I can basically handle this system the same way I handled this system here. It's just that what I called x and y here, I'm going to call something else here. So what I want to do is first say the directions I will consider are the directions of motion for this block. Which way could the block move? Well, the first way it can move is along the ramp, right? It can move up and down the ramp. That direction I call parallel, which means parallel to the surface of the ramp. So that is down and to the left or up and to the right. Those directions are called the parallel directions. Just like here, when you consider this block, it's on the surface, and the block can move either to the left or the right. That's parallel to the surface. Same thing here. If I forget, if I look very closely and I'm not far away from the ramp, I don't see the ramp, I just see that the block is on a floor. and the block can move along the floor. And that means it can move parallel to the floor. Now if I zoom out and I look, I see, oh, the floor is actually at this weird angle. But who cares about the angle? We're talking about when this block moves, it can either move parallel to the floor or the other is perpendicular. I'm sorry. Which just means it can move off the floor or into the floor. So in our first example here, parallel meant the x direction, perpendicular, up and down, means the y direction. Same thing here. Parallel means along the floor. Perpendicular means up off the floor, like this way, or down into the floor that way. So again, I have two perpendicular directions, but instead of calling them x and y, I call them parallel and perpendicular. And now what I'm going to do is all my equations will either be in the parallel direction or the perpendicular direction. Because I know this block, when it moves on this ramp, it's either going to move in the parallel direction or the perpendicular direction. Just like with the first example, it was either going to move in the x direction or the y direction. In that case, I happen to know it was in the x direction, so when I solve the equations, I do it all in x. Here, it can either move in the parallel direction or the perpendicular direction. Now, when I look at it, I know it's going to move in the parallel direction. It's going to slide along the floor, which is the parallel direction. So when I do F equals ma, I'm going to do F equals ma in the parallel direction. So all that means to me is, just as with this example, every vector has to be in x and y directions, and if there happens to be one that's at an angle, I need to break it up into x and y components. For this new example, I don't want x and y anymore. What I want are all my vectors to be either in parallel or perpendicular directions. So when I do my components, instead of trying to find an f1x and an f1y, I'm going to find an f1 parallel and an f1 perpendicular. That's it. It's just a different name of a direction, but it's the same technique. So if this is true, let's look at my problem. What are all the forces acting on my block? There's only one force sitting there, gravity. Which direction does gravity pull? Gravity always pulls vertically downwards. That's a y-directional force. Well, since I'm on this ramp, x and y are now bad to me. In this first example, because everything was horizontal, x and y were good. I liked x and y here, and it was the angles that were bad. But now that I'm actually sitting at an angle, and I'm going to move at an angle, x and y stuff are the things that are bad. And so anything that's in the x or y direction, I need to break up into the new directions. And of course, gravity being a y-directional force means I have to find the component of gravity in the parallel and perpendicular directions. So what I want to do, I want to find the amount of gravity in the parallel direction. So parallel has that symbol, and perpendicular has that symbol. And I want the force due to gravity in the perpendicular direction. Okay. But here's the key. How do I do it? Let's focus in on the object and see what to do. So here's my object. And we've got gravity pulling straight down, mg. And what I want to do is take this mg, this force due to gravity, and make a triangle out of it such that one side is parallel to the surface and the other side is perpendicular to the surface. It's just like my first example over here. Notice this had a perpendicular side and a parallel side. I call the parallel piece X and the perpendicular piece Y. Well, now I want to do the same thing here. So the way you do it is one side. Remember, parallel means parallel to this surface. Here's the surface. Perpendicular to the surface means perpendicular to that line. So my first line has to be perpendicular to it. That I call the amount of gravity perpendicular. And then I need to complete this triangle with a line which is parallel to this surface. So here it is. That line there is parallel to this line here. And so that's my amount of gravity parallel piece. And now I have my triangle. Here is my 90-degree angle, because parallel and perpendicular are perpendicular to each other. MG, that's the hypotenuse. The only thing left is I need one angle here. Once I have one of the angles, then I could do sine or cosine to get the two components. Here's the rule. I won't prove it, because who cares if I can prove it. The rule is this. This angle, this 30-degree angle here of your ramp, happens to be the same as this angle here, this top angle. So these two angles are the same. Always. And so there we go. I now have my triangle. Let's look at the triangle by itself. Here it is. Perpendicular piece, parallel piece. This angle here is 30 degrees. This side is MG. Here's my parallel. Here's my perpendicular. So looking at the triangle, how do I get FG parallel? Parallel side, that's this side down here. That side is opposite to my angle, and opposite means sine. So it's M times G times the sine of the angle, 30 degrees in this case. All right, well, what's M times G? M is 10, that's the mass of the block. G is 9.8, always positive, times the sine of 30. I'm going to plug this into my calculator. 98 times sine 30, and I get 49. One last step before I move on is directionality, positive versus negative. Is the amount of gravity which points in a parallel direction, is that negative or is that positive? It's the same as asking in my first example here, I found F1x and F1y. Well, F1x is the amount of my 30 Newton force, which points in the x direction. I called it positive 15 because it was pointing to the right. And the amount of F1y I called negative because the amount of that 30 Newton force pointing in the y direction was pointing downwards. And downwards I called negative. Same thing's going to happen here. I have a parallel piece and I have a perpendicular piece. Okay. If this is my FG, then the parallel piece points down and to the left, and the perpendicular piece points downwards like this. So I need to call some direction positive and some direction negative. Thankfully, it's arbitrary. You get to choose which side you want to make positive. So look at your ramp. In the parallel direction, you can either go down and to the left this way, or you can go up and to the right this way. So one of those is positive, one of those is negative, and it's up to you what you want to call positive. Now, for me, I'm looking here. I happen to know this block is going to slide down the ramp. Since I know it's going to move down the ramp, let me call down the ramp positive. Because if I don't, then that just means I'm going to have a negative in my answer. You can do it. That's perfectly fine. Just tell me that's your negative. For me, since I know the block is going to move in this direction, why not just call that the positive direction? So the way we usually handle it, so that people who are reading our work understand what we're doing, what we do is we're going to say this direction is positive, and then I'm also going to call downwards into the ramp, the perpendicular direction, that's the positive for that direction. So if you relate it to x and y, in the x direction, I call to the right positive and to the left negative. Here in the parallel direction, I call sliding down the ramp positive and sliding up the ramp negative. And then in the y direction, I called up positive and down negative. For this particular example, in the perpendicular direction, I'm calling into the floor positive and off the floor negative. That's my own choice. If you would make a different choice, you're free to do it. Just show on your picture, like I did here, which way is your positive, and that's fine. What will always be true is the numbers will always come out the same numbers. It's just that if you choose sliding up the ramp to be the positive direction, then when you give your answer, you're going to have a negative answer and I'm going to have a positive answer. But the number we have will be the same number. So that's good. So arbitrarily, purely because I happen to know in this case the block will move down the ramp, I'm calling down the ramp to be the positive answer. It doesn't matter. I could have chose the other way. This is just what I chose. All right, so there's my gravity parallel piece. I now need gravity perpendicular piece. So looking at my green triangle here, perpendicular side is a side adjacent to my angle, and adjacent means cosine. So m times g times cosine 30. M is 10, g is 9.8, cosine 30, and we get 84.9. All right, so there we go. I've taken my problem. All the forces acting on my problem, I've now broken up into parallel and perpendicular pieces. Once that's done, all that's left is to solve the problem. What's the problem say? I want to know the acceleration. Which direction will this block move? Parallel direction. So looking in the parallel direction, I have the sum of all the forces in the parallel direction is mass times acceleration. What do we have? I've only got one parallel force here, 49, equals mass, 10, times acceleration. So, the acceleration is 49 over 10, which is 4.9. And there we go. A very, very important example. When you're given problems in F equals ma, in Newton's laws topic, the block which has the forces acting on it will either be on a horizontal surface, it could be up against a vertical wall, or it'll be on a ramp. Those are the three options. The first example, of course, had it on a nice horizontal table, and that means all of your forces have to be x and y stuff. This example had the ramp. The only difference between the two is that instead of looking in x and y direction, I'm looking at these other two directions, which I personally call parallel and perpendicular. Textbooks, if you look in a textbook or online, they may call it x prime and y prime, or x2 and y2, or some other names. They're just names, though. For me, calling it parallel and perpendicular helps me to realize what they mean. If I call it x prime and y prime, well, that just like a basic arbitrary name that doesn't have meaning to me. But if someone says the parallel direction, well, I immediately understand what they mean. It's the direction which is parallel to the surface, parallel to the floor. And perpendicular means perpendicular to the floor. So I could visualize that direction. But if you tell me it's in the x prime and y prime direction, well, I have to know what you mean by that. That's why I've chosen parallel and perpendicular. If you're looking off of some other reference and they don't use those terms, that's fine. They're just using other names. The technique is what's important. Anytime you solve f equals ma, you have to have what's called a coordinate system. What are your main directions? For most problems, like this one, your directions are x and y. And so every single force in the problem, get x and y pieces. And then do f equals ma on that. Probably looking at the x direction or the y direction. If, however, you're on a ramp, all of a sudden, x and y are now bad. And instead, you want these two other directions, which I'll call parallel and perpendicular. But you're still doing the same thing. You're going to take all the forces acting on your system and now get parallel and perpendicular pieces. Once you have all of those pieces, you now do f equals ma with those pieces. So please try to see it as the same type of thing. This isn't a different technique. This isn't way more complicated than the other example. All you've done is looked at two other directions using the same method. You're using parallel and perpendicular as the directions, as the symbol names, but the steps you go about solving the problem are the same. Let's look at another example. Let's look at the perpendicular wall problem. Here's a block, 10 kilogram block. I apply a force of, let's say, 20 newtons. And let's say that force happens to be at an angle of 30 degrees with respect to the vertical. So it's almost like you're trying to slide this box up the wall. That's what you're trying to do. So, and again, we're not talking about friction yet. So for this problem, what is the acceleration? All right, well, first step, now that I recognize you have the ability to have different directions, what are the important directions for this problem? Well, which way can the block move? Well, it's either going to slide down or it's going to slide up. So that means the y direction is important. So because the y direction is important, I want to break everything into x and y components. Okay, in order to do it, I first need to know what are all the forces in my problem. Well, obviously, we have this force here. Call that the applied force, Fa. But is that the only force in my problem? For instance, if I stopped pushing on the block, what would happen? If I didn't push on this block, the block's going to fall down to the ground. And the reason it falls down to the ground is because gravity exists. So there must also be gravity. And gravity, again, is always perpendicularly downwards. All right, so those are the important forces. I'm applying some force to the box. Gravity is trying to pull the box down. There's also a normal force, but I'm going to leave normal force for when we get into friction, because I just don't want to, mess up my picture with multiple forces that aren't going to be important for us. They will be important later, but for now it's not important, so I'm not going to draw it. These are the things which will make the box move. All right. Well, are any of my forces not in the right direction? That is to say, are there any forces that are not in the x and y direction for this problem? Because remember, the first question I asked was, what are the important directions? And I said x and y. So if x and y are the important directions, then I say, are there any forces that are not in x and y? Sure, my applied force, that's at an angle. So all of the forces which are at angles, I need to break into x and y components. All right, let's do it. So applied force needs an x piece, and applied force needs a y piece. Let's look at my applied force. Here it is here, drawn again. There's the vertical side, there's the horizontal side. So this is x, this is y. 30 degrees is here, and this is 20. All right, so looking at my triangle, what do I have? I want the x piece. The x side is the side opposite to my angle, and opposite means sine. So 20 sine 30. However, before I keep going, is this positive or is this negative? Well, which way is my applied force pushing? It's pushing up and to the left. So in the x direction, it's pointing to the left. I'm going to call left negative. So he's negative. So negative 10. All right, what about the y side? The y side is a side, in this case, adjacent to my angle. Adjacent means cosine, so we've got 20 cosine 30. Positive or negative? Well, the applied force is pushing up and to the left. In the y direction, it's up. Up is positive for me, so he's positive. And then 20 cosine 30, we have 17.32. Those are all the forces which are in angles. And so now I have all of my forces in x and y components. FG is already in a y direction. FA, I've now split. There's no other forces I see. So now I do, looking in the y direction, because obviously that's the way the block is going to move. It's going to move in the y direction. So looking in the y direction, my equation, the sum of all the forces in the y direction is MA. All right, so what are all my y forces? Well, of course, I've got my applied force in the y direction is positive 17.32. I also have gravity pointing downwards, so minus gravity. And that's all the y forces in my problem. So set that equal to mass times acceleration. All right, well, in order to solve for A, I just have to know what Fg is, but we know the force due to gravity is always mg, every time. So 17.32 minus m, 10, times g, 9.8. And again, remember, when we say g for Newton's laws, that's the acceleration due to gravity, we always call it positive. Gravity is negative when we talk about the direction of the force. It's downwards. But the number g is positive 9.8. So don't put an extra negative in there for the 9.8. The negative is on the outside for the direction. The number g is positive 9.8 always. All right, so here's my equation. 17.32 minus 98 equals 10 times A. A then must equal 17.32 minus 98 is negative 80.68 divided by 10 to get the 10 on the other side. So we get negative 8.07. So what does that say? that tells me that even though I'm pushing up on this box, I'm not pushing hard enough. So the box will still slide down the wall. It'll slide down with this acceleration of -8. So there we go. We've now seen an example of all three styles. Our first example was a block on a horizontal surface. The important direction here is x and y direction, x in particular. So all the forces must have x and y components. Once I do that, I then say, which direction will my block move? X direction. So F equals ma in the x direction. Example 3 was a vertical surface. We're against a vertical wall or something like that. The important directions are x and y again. So again, every force must be either x or y components. Any force that isn't already, break it into x and y pieces first. Once that's done, I say, what's the direction of motion of my block? In this case, it'll move in the y direction. So F equals ma in the y direction will give me my acceleration. And then the most complicated of the three is the inclined plane, the ramp. What's the important direction here? Now it's not x and y, it's what's called parallel and perpendicular. Okay, so all that means is any force that's not already in the parallel or perpendicular component or in direction, I have to break it up into parallel and perpendicular components. In this particular example, the only force here was gravity. Gravity is a y force. That's bad. So take the y force and give me parallel and perpendicular pieces. And we saw how to do that. I had to erase it, but we saw how to do it earlier. You take the triangle. The gravity is a hypotenuse, straight down. Then one side is perpendicular to the floor. The last or the third side is parallel to the floor. And now you have a right triangle. The parallel side, the perpendicular side, you get your components. And then you say, once all that's done, I've now got all my components laid out. You ask the question, which direction will my block move? For this one, it'll move in the parallel direction. So I use F equals ma in the parallel direction. So you can see that the method is the same for all three styles. There's a little uniqueness here and there in actually doing the steps, but each step is identical. Definitely you need to practice this example too. I'm going to give another video later with some more examples with more forces involved. And then eventually we'll start dealing with friction as well. See, how does friction fit in? But with this information, you should be able to take the practice problems and the homework problems that are posted on Canvas and try to work your way through them. They're going to have maybe a couple of more forces. If they do, don't worry about it. They're just extra pieces to plug into F equals ma. Because that F equals ma means you add up all the forces in this direction. So if you got 10 forces, then you're going to have 10 F's in it. That's fine. You're just adding them. Or, of course, subtracting if they're in the other direction. So slowly work your way through these. Of course, if you have questions, feel free to email me. I'll be happy to look over what's going on. As I said, look for another video coming up with some more example problems done. And then a future lecture on friction itself. How does friction get involved? Which will be the final equation we need to know for Newton's laws. Thankfully, it's only two, F equals ma and what we do with friction. And what you're going to find is friction doesn't make it all that much more complicated. All it's going to do is plug in one new force, which means F equals ma. There's one other F in there. That's all it is. It's just that you need to calculate what this F is first. So thankfully, while friction may seemingly make a problem more complicated, you're going to find that it really doesn't. It just makes you plug in one extra f somewhere. Well, that's not a big deal. So anyway, I hope this is helpful, and I'll see you next time.